Okay, we're going to do a review of test 2 today, and we're going to go over this 2001 test 2 from fall of 2001, and that will happen in a second, but first I want to go ahead and talk about what's online for you to look at. So first we have this list of old test 2 problems that you can ignore, meaning that if you look at all these old tests, that some of the questions are questions that are going to come up on test 3 that you should ignore for now as far as studying for test 2. And some of them are material that we haven't covered, which you should also ignore. So just look at the list that's given there. And then there's a list here of old test 1 problems that you might want to look at from the old test 1s that were in material for test 1. And that's because we didn't have them on test 1, but they are material for test 2. So you might want to look at that list as well. And then you have lots of problems you can practice with here. You have the old quizzes, or many of them, 11 of them here, that include some max-min questions, but also arc length questions, quiz 5 here, quiz 5 here, and your quiz 6 here. I mentioned that because when we do the fall test in that moment from 2001, that does not have any arc lengths in it. And I haven't written the test yet, but arc length is something I usually have on tests, so you do want to look at those. And of course, you have all the old tests to look at and answers for them, as well as worked out solutions for many of the problems. And in particular, I saw a lot of max-min questions there that are worked out for you. So let's look over the test 2 from fall 2001. So we have a function for the first problem that looks like this, and we want to know the limit of this function as xy approaches the origin. Well, first, does it exist is the real question. If so, what is it? And if not, why not? So we had two ways to approach this. One is just to try different paths going to the origin and see if you can get two different values for the limits, showing that the limit value depends on the path you take, which would mean the limit does not exist. If you try different paths and seemingly you're always getting the same limit, then you need to do something else because you're not going to be able to show infinitely many paths going to the origin give you the same limit very easily. At least nothing that we've done in the class does that. So what you're going to need to do is to do a different approach, and that's where we use polar coordinates to show a limit does exist. So start out by trying different directions toward the origin to see if you can get two different values, and if you can't, then try polar coordinates to show that the limit does exist. So if you try different directions here, it isn't too hard to come up with two different directions where the limit isn't the same, so you're going to have the limit does not exist. So the answer here is no, the limit does not exist. And the reason is, well, you can do different directions, but the way I did it was to go ahead and look along the y-axis. So on the y-axis, x is 0, so this won't be here, and you'll just have minus 3y squared over y squared, which is minus 3. So this means, unless you're at the origin, if you're on the y-axis, you're just going to have minus 3 for the value. And as you approach the origin, well, whether you're going in the positive direction or negative direction, if you're going from the positive or negative direction toward the origin, you're going to be getting minus 3 because f is always minus 3 on the y-axis other than at the origin. So we get minus 3 as we approach the origin along the y-axis. If we go along the x-axis where y equals 0, these will go away, and you'll have 2x cubed over x squared. So this will just be 2x. And so the value of our function is 2x on the x-axis, and except for at the origin where the denominator is 0, so that's not going to work. But as x approaches 0, so as xy approaches 0, the origin here, 0, 0, then along the x-axis we're going to be getting 0 because 2x is getting small as we approach the origin, and 2x will go to 0. So we get 0 along the x-axis. Again, it doesn't depend on which direction we're going, whether we're going from the right or left towards 0 on the x-axis. We're going to be getting 0 for that limit. And since minus 3 does not equal 0, These limits are not the same, so the limit here does not exist. So this limit is going to not exist. Again, because we approach the origin in two different directions, we get two different limits. So the next question is about taking derivatives, and here you're asked to compute this. So it's a derivative with respect to y twice, and then a derivative with respect to x twice. The order in general doesn't make a difference. If you follow the direction that I'm giving it to you, where you do the y twice first and then the x twice, it'll be easier because I'm going to make sure it comes out that way. So first we want to do the derivative with respect to y. So I get 2y for this, so 2y times x cubed. This will give me a 3y squared. So I'm going to get the minus 3y squared times x squared. This is just going to be 0 because this is a constant with respect to y. And then here, this is a constant, so this is going to be a constant times y. So when I take the derivative, the y becomes 1. We just have cosine of x cubed. Now this is a little ambiguous as to what this means. It could be cosine of x cubed, or it could be cosine of x cubed. Either way, it doesn't make any difference because we're about ready to take a derivative with respect to y again, and this is a constant. So this is just going to be 0 when I take the derivative with respect to y. So taking that next derivative with respect to y, we're going to have this y is going to become 1, so we have 2x cubed. This y squared becomes 2y, so we'll have minus 6y x squared. And again, this will be 0 because it's a constant. We still have to take the derivative with respect to x twice. So taking the derivative with respect to x, the x cubed becomes 3x squared, so this is 6x squared. This x squared becomes 2x, so we get 12xy. And so we have 6x squared minus 12xy, or yx doesn't make any difference. We want to take the derivative with respect to x again. This will become 2x, so 12x here. This x will become 1, so we just have minus 12y. And I rewrote it this way, and I've told you in the past that I didn't care if you write it this way or this way. But of course, if you have a multiple choice test on this, you're going to have to find whatever form I put it in for the answer. So it might look like this, or it might look like this. This is an integral question. We're integrating, and we have a piecewise function in a certain region here, and we want to ignore this because this is integration problem, and that's for test 3. The next question is also an integral problem. It's a double integral, and we want to ignore that as well. So now problem 5 is about finding an equation for the tangent plane to a certain surface at a certain point. Now you can plug this in, the minus 3, the 1, and the minus 1. This will multiply together to give you a 3 like you want. So this is a point on the surface, and we want to know the equation of the tangent plane at that point. So our method was to bring everything on one side and call that capital F, and then take the gradient to get a normal to the tangent plane. So I'm not going to actually take the 3 on the other side. You don't have to do that. You could put a minus 3 here. We're about ready to take partial derivatives, and the derivative of 3 with respect to any variable is 0, so it's not going to come up. So it's okay to have a constant and just take on this side and just take the function to be that. But in any case, whether you put the minus 3 here or not, I want to take the gradient of this. So I take the derivative with respect to x. I'm just going to have y squared z cubed. When I take the derivative with respect to y, this becomes a 2y, so I'll have a 2xyz cubed. And with respect to z, this becomes a 3z squared, so I'll have 3xy squared z squared. So that's the gradient of f. We want to calculate it at this point. So I plug in minus 3 for x, 1 for y, and minus 1 for z. So we plug it into here. So we have 1 squared times a negative 1 cubed. That's giving me a negative 1. Then we have minus 3 here. So that's minus 6 times this 1 is minus 6 still. Then you have minus 1 cubed. So that's going to give me a plus 6. Here we have minus 3 for x. So this will be a minus 9 when I multiply times 1, so minus 9. So the gradient of f at this point is minus 1, 6, minus 9. Now we want to use that as the normal to the tangent plane, which means we want these -1, 6, and -9 here to be the coefficients of x, y, and z. So for our tangent plane, we're going to use a -1 times x, a +6 times y, and a -9 times z. And we want that equal to something. And we figure out where this number is, what this number is, by plugging in the point -3, 1, -1. So I know this has to be a point on my plane. So I plug this in, I get minus a -3, which is 3, plus 6 times 1, which is going to be 9 when I add that all together. And then I have -9 times -1, so it's plus another 9, and that's giving me the 18. So I got this 18 by taking this point up here, the -3, 1, -1, and plugging it into this expression here. That gave me the 18. So that's how I knew where 18 was coming from. And this then is the equation of the tangent plane to that surface up there at the point -3, 1, -1. So here we have a certain surface that's given to us, z equals f of x, y. And we're at a point on that surface where x equals 1, y equals 1, and z equals -1. Again, we could plug in x and y are 1. We're going to get 3 minus 4y. Z would be -1. So this is a point on that surface. And we're going to put a drop of water at that point on the surface. And the problem is, in what direction does the drop of water start to move? And I say to express your answer as a vector AB like this, meaning if you look at the shadow in the XY plane, what direction is that shadow moving in? So to explain this better in a picture, this is not the particular surface we have. This is a picture we looked at earlier in the course. And what I want you to do is imagine putting a drop of water right here, where this point is on the surface. And the point is that the drop of water will go in the steepest direction here, in this direction. That's the same as the direction of the directional derivative that gives you the least directional derivative. So it's the least value of the directional derivative, the minimum directional derivative. It's going in that direction that gives you that minimum value for a directional derivative. And we had a theorem that said if you want the least value of the directional derivative, you go in the direction of minus the gradient. So that's what's down here. You want to go in the direction of minus the gradient. So it's this vector I'm looking for that's telling me I want to go in this direction for the water. So I'm looking for minus the gradient. And that then will be what we're looking for our answer. Notice, again, z is f of x, y, some function, and this gradient in the xy plane. So here we have z equals f of x, y. We want to take the gradient of this f of x, y here, this 3y squared minus 4x squared. So let me call that f. I compute the gradient by taking the partial derivatives. The derivative of this with respect to x will be 0 minus 8x, so minus 8x. And the derivative with respect to y will be 6y minus 0, so 6y. So this is the gradient. We're at this point where x and y are 1, and those are really the only two variables I'm interested in at this point. So I'm going to plug in 1 for x and y. And then this becomes minus 8 and comma 6 here. So minus 8 for the first component, 6 for the second component. So this is minus what we want to do. We want to go in the direction of minus the gradient. So we want to go in the direction of 8 minus 6. I went ahead and took out a 2 from this because that won't change what the direction is. So instead of 8 minus 6, I'm going to go in the direction of 4 minus 3. So 4 minus 3 is what I'll use for the direction of the water going. So again, minus the direction of the gradient, but if I take out a positive 2, that's the same direction, so 4 minus 3. You can keep this 8 minus 6, that would be fine. In the end, I want a unit vector, and the unit vector, if I say unit vector, you have to divide by the length of this, and the length of this is 5 because 4 squared minus 3 squared is 25, and the square root of 25 is 5, so I'm going to look at 1/5 of this to get a unit vector. So I want 1/5 of that, and so the answer is going to be 4/5 comma minus 3/5. That's the direction you want to go in if you want a unit vector. If I'd kept this 8 minus 6, the length of that would be 10, so I'm taking a 1/10 out here. and you would have 8/10 over minus 6/10, which reduces to the same thing. So this is the answer to the question. This is a problem involving the chain rule, and this is also something that we decided not to do in this course. Global max and min, definitely something we want to be able to do in this course. We have a function of two variables that's given to us. We're inside a circle of radius 2 centered at the origin, and we want to find all points x and y in this circle or on this circle, where the max and min values occur and what those maximum and min values are. So I'm going to handle first the points that are not on the boundary but inside the circle, where x squared plus y squared is less than 4. So for that, we take the partial derivatives of f and set them equal to 0. So with respect to x, we have 3x squared plus 8x minus 3. And with respect to y, we just have 8y coming from this term. We want to know where both of these are 0. We want points x, y, where both of these are 0. We see y is going to have to be 0. This we are going to have to factor in order to figure out what's going on with x. So this does factor. It factors as 3x minus 1 times x plus 3. You can see that we have 3x squared minus 3. And then the middle term is going to be 9x minus x is giving me the 8x. So where does this equal 0? This equals 0 at x equals 1/3 and at x equals minus 3. Well, y was 0 and x was 1/3 or minus 3. So when x is 1/3 and y is 0, both of these are 0. And when x is minus 3 and y is 0, both of these are 0. So those look like good points to look at, except for this point is really not a point to look at, because if we go back to our equation here, our inequality, 3 squared plus 0 squared is not less than or equal to 4. We're going to have 9 here. And so this is not a point in our region S, and so we don't want to consider it. So you should ignore this point. I'll get rid of it. And really the only point to consider in S is 1/3 0 for these partial derivatives being 0. So we get just 1 point, not in the boundary, that's an S. Let's look at the boundary now. On the boundary, we have x squared plus y squared equals 4. So we can replace y squared with 4 minus x squared, just put it in here. Which will get us 16 minus 4x squared, and this will go away. And so you get x cubed minus 3x plus 16. I'll do that a slightly different way, but I'll go ahead and take the 4x squared plus 4y squared, take the 4 out. And notice on the boundary, x squared plus y squared equals 4. So this just becomes 4 times 4, 16. And we had the same thing we just said a second ago, x cubed minus 3x plus 16. So this is what I'm calling g of x. And we want to keep in mind that since we're inside this circle, x is between minus 2 and 2. So again, g of x has the property that if I take any point on the boundary, that the value of f of x, y is the same as g of x. So we have a max-min question now in single variable, just one variable x here, and we're in a closed interval from minus 2 to 2. And so the way we find the max-min for this, the global max-min, is we go ahead and take the derivative of g, set it equal to 0, look at what points are inside this closed interval, and look at those points that we get from taking the derivative, setting it equal to 0, as well as the endpoints. And those will give us the points we have to look at for the global max and min. So we want to take care of these two endpoints, so I'll include those as boundary points we want to consider up here, 2, 0, and minus 2, 0. So the y coordinates coming from the fact that if x is plus or minus 2, we get a 4 here plus y squared equals 4 on the boundary, y will be 0. So let's take the derivative. G prime of x is 3x squared minus 3. We want to set that equal to 0. You can see x squared will be 1, so x is plus or minus 1. So we get these two values of x we want to consider on the boundary. Notice when x equals plus or minus 1, this will be 1 when we're squaring it here, and y squared then will be equal to 3, and so y will equal plus or minus the square root of 3. So when x equals 1, or x equals minus 1, we get plus or minus the square root of 3 for y. So that gives us, looks like 7 points here, 2 here, 2 here, 1 here, 1 here, and 1 here. So we have all 7 points to look at, and to get the global maximum for this problem, the global maximum of f of xy, we want to just plug in each of these points to see which one's the largest, and for the global minimum, plug them in and see which one's the smallest. But we can tell the values at 1 and minus 1 by just taking x equals 1 or x equals minus 1 into our function g, because here we're on the boundary as well as here. So we just plug in the x. We plug in x equals 1, we get 1 minus 3, which is minus 2, plus 16 gives me 14. So at these points, the value of f is just going to be 14. For minus 1, I get minus 1 plus 3, that's plus 2, plus 16 makes 18. So at these 2 points, the function has the value 18. At 2, we get 8 minus 6 plus 16. That's going to be 18 again at 2, 0. And at minus 2, 0, we'll get minus 8 plus 6 plus 16. And that'll be 14 again, like we had at this point. So we have 14 at these and 18 at these. So let me go ahead and be a little organized here and just go ahead and make a table. But first, g of 1 equals 14, g of minus 1 equals 18, like we said. Let me go ahead and make a table here. So these were the points from the previous slide. And as we said, this is 14, this is 18. We got the values here and here as well. This was 18 and this was 14. So we get 18 there and 14 there. So we need to plug in 1/3 0. So this will be 0. We have 1 over 27. We have 4 over 9, which is 12 over 27. So the 1 over 27 and 12 over 27 gives me 13 over 27. And then when I plug in 1/3 here, this will be minus 1. So we have 13 over 27 minus 1. And 13 over 27 minus 1 is minus 14 over 27. So that gives me the value there. And that's an important value to have because that's clearly the minimum value here. So that's the minimum value at 1/3 0. And we have the maximum value 18 occurs at 3 points, 2, 0, minus 1, plus or minus the square root of 3. So we can summarize by saying the global maximum is 18, and it occurs at the points 2, 0, and the point minus 1 plus square root of 3, and the point minus 1 minus the square root of 3. The minimum, the global minimum, is this minus 14 over 27, and it occurs at the point 1/3 0. So that finishes this problem. We got the global maximum, global minimum, and where they occur. The next problem is a local maximum question. And I've given you not just the function, but I have given you all the derivatives we need. We have f sub x, f sub y, as well as the f sub xx, f sub xy, and f sub yy. And we want to find what the, well, just where the global max and min are, as well as the saddle points. So to find where they're at, we first are going to just set both of these equal to 0. Again, we want both of them equal to 0. And you can begin with either way here. I'm going to work with this side and say either y is 0 or y equals x here. So either this is 0 or this is 0. So if y equals 0, again, that makes this 0, but we need this to be 0 also. So if y is 0, this is x plus 1 times x minus 1. So you can see x has to be plus or minus 1. So that gives us 2 points. We get the minus 1, 0, and we get 1, 0. If y equals x, to make this 0, then we want to plug in y equals x over here. So this will be minus 4x here. One possibility, x is negative 1, and then we'll have x minus 4x minus 1, or minus 3x minus 1 is equal to 0. So we have the x is negative 1, and since y equals x, that'll also be the value of y there. Or we have minus 3x minus 1 equals 0 from here, which is minus 3x equals 1. And so dividing by minus 3, x is minus 1/3. But again, since y equals x, y will also be minus 1/3. So we have 4 points, the minus 1, 0, the 1, 0, and the minus 1, minus 1, and the minus 1/3, minus 1/3. So those are our 4 points to consider, our 4 critical points. And now we want to know whether there is local maximum there, or is there a local minimum at each of these, or is there a saddle point? So I'll make a table in a second for these as well, but let's go ahead. We need to look at this d function. This d function, again, is f sub x x times f sub y y minus f sub xy squared. So we want to uh, use the values that were given in the problem for those. So I told you what f sub x x was in the problem, f sub y y, as well as f sub x y. So we want to use those values that were given to us in the problem. And so we got the d here, and now we can go ahead and make this table. We have the 4 points that were critical points. I'm going to go ahead and calculate f sub xx. We only need that when d is positive, but f sub xx was this 2y here, and that's easy to see. That's just 0, 0, minus 2, and minus 2/3. So I'm just going to get 0 there, 0, and then minus 2 and minus 2/3. So that's the value of f sub xx. And now for the value of d, I want to go ahead and plug these into here. Notice that if y is 0, this is 0. So this will be 0 when y is 0. When x is minus 1, I'll have minus 2. That's 0. So minus 2 squared will be 4, and so I just have minus 4. When x is 1, again, this is 0 because y is 0, and this is 0. So this should be 2 squared. And we'll get minus 4 again. Now, when x is minus 1, this is going to be 0. Minus 4 times minus 1 will be 4. Minus 4 is 0. So this will be 0. So with x and y both minus 1, I'll have minus 2 plus 4. This will be 2 squared again, and we'll have minus that 2 squared, so minus 4 again. Now we need to plug in minus 1/3 and minus 1/3, so that's clearly going to be different. What do we have? We have a minus 2/3 here. This is going to give me 4/3 when I plug in x is minus 1/3. So 4/3 minus 4. 4/3 minus 4 is 4/3 minus 12/3, so minus 8/3. So we have minus 8/3 for this. We have a minus 2/3 for this. So that's going to give me 16/9. 16/9. So keep that in our heads. We have 16/9 for this. Coming over here, we're going to plug in minus 1/3 and minus 1/3 here. So we have a minus 2/3 plus 4/3. Minus 2/3 plus 4/3 is 2/3. We square that, we're going to have 4/9. So this is 4/9 after I square it. This was 16/9. 16/9 minus 4/9 is 12/9. So 12/9, we can take out a 3, that's 4/3. You don't necessarily need to do all that work. You need to see that it's positive, but it is positive there. And so these will be saddle points because d is negative. D is positive means that it's a local max or a local min. And since this is negative, it's concave down in the x direction, so this will be a local max. So relative max occurs at minus 1/3, minus 1/3, and saddle points occur at these points, minus 1, 0, 1, 0, and minus 1, minus 1. And so that finishes this problem. I want to do a quick overview of everything we've done that's going to be on this test. So again, you should know arc length. Even though there wasn't a problem like this on this test we just went over, the 2 quiz 5s, again, on the home page for this course, and the quiz 6 that you took on that page, all our arc lengths worked out, so you can look at that. And also, velocity, acceleration, and speed, not quite as difficult, but you should be able to answer a simple question related to velocity, acceleration, and speed. This doesn't mean much. I just mean that if you're taking a limit, say we're approaching the origin like we usually do, or even some other point, you got to look at all the different directions you can approach it. And if 2 of those directions give you something different, then you know the limit does not exist. If they all give you the same, then you know the limit exists, but it's hard to try many different directions. And what we typically do for that is to go ahead and use polar coordinates to show a limit exists. Now, you should be able to compute directional derivatives. Remember, it requires using a unit vector because we want to take a unit vector dotted with a gradient. The largest value of the directional derivative of f at a certain point is going to be the length of the gradient at that point. And the direction you want to go in to get that largest value, the direction for that directional derivative is the direction of the gradient. And like we saw earlier, if you want the direction that gives you the least value, you go in the direction of minus the gradient. And the value of that least value for the directional derivative will be minus the length of the gradient. The gradient at a point on the surface, so if you have f of x, y, z equal to 0, and I take the gradient of capital F at a certain point on that surface, then it's going to be perpendicular to the tangent plane there. So it's normal to the tangent plane, and you can figure out the equation of the tangent plane from that. You could also figure out the equation of the normal line to the tangent plane at that point. We've had some problems like that because the normal line will be going the direction of this gradient, the normal vector. I mentioned this in this review because I usually mention it, but we're not doing the chain rule, so we can take that off. So when we're dealing with the boundary, we've got to remember to change the problem to a single variable, meaning that we have a function f of x, y. We rewrite it as a function in just one variable, usually x, so g of x. We have a function then in one variable to deal with, and we can use the calculus we learned before this course to handle it. And don't forget to use the endpoints when you're doing this. So you end up with trying to find the max or min of g of x in a certain closed interval. You got to check what happens at those endpoints. This again is the value of d. It's f sub x times f sub y minus f sub xy squared. And you would need that to memorize this for the test, except for this will be an online test where I'm going to let you use your notes. So instead, you might want to have that in front of you before the test so you know what d is. You only use critical points when you're trying to use d here. And this is just saying the product of f with respect to x and y are both 0. And then as long as the product of f sub x and f sub y are both 0 at the point, you have a critical point. And then you use this d function only at those points. If d is greater than 0 and the second derivative with respect to x is greater than 0, then you have a local minimum. So this tells you it's a local minimum max. This tells you it's concave up in the x direction, so it's going to be a local minimum. Similarly, if d is greater than 0 and f sub xx is less than 0, so it's concave down in the x direction, you'll have a local maximum. And if d is less than 0, you have a saddle point there. So again, this is telling you the location of them. The actual value would be what you get when you plug into the function f. But you'll have a saddle point at when d is less than 0 at those points where critical points where d is less than 0. So when d equals 0, again, that means that the teacher shouldn't have asked you that question. Anything can happen. It can be a local max, a local min, or a saddle point. For maximizing or minimizing a function, we have a way of doing that called Lagrange multipliers. And Lagrange multipliers involve something like this. But again, we did not do Lagrange multipliers, so we can take that off this list for the review. So your review only includes the previous stuff I've listed here. And that concludes then this lecture and the review.